Welcome also from my side. Thank you for the introduction, and yeah, great to talk about one of my most favorite topics about Agile electronics and how we can actually implement it in real life. And let's start right into it. But before we go into the topic, I would like to also get a bit of information about you, about the audience of today. So please feel free to scan the QR code or enter the URL in your browser and just answer on which role you have in your company and what your main interest is about the topic of Agile electronics. And I'll try to integrate that into the webinar. So getting the first answer. Great, thank you. So let's start right into the topic. At the start of the project, how often do you stand in front of detailed planning Gantt charts that exactly describe the process of the project you're trying to implement? And how often did those Gantt charts prove true during the process of the project? How often did you experience change requests that resulted in delays at the end and increased the cost of the projects? Not only, but especially in hardware development, we are used to detailed planning at the beginning of a project. The goal that we have is always to get an estimation about the duration and the cost of the project that is as realistic as possible. But unfortunately, we as humans are incredibly bad at estimating durations of work tasks. There is the famous cone of uncertainty, which is on the slide. And it basically says that if a project takes 1 year in reality, our early estimations at the beginning of the project can vary between 3 months and 4 years, according to statistics. And from experience of probably most of us, we know that we tend to underestimate work instead of overestimating it, or there can be unforeseen obstacles on the way that also increase the project time. So we often approach the planning of the project in a way we wish it would work, ignoring that the fact that we as humans don't naturally think or operate that way. So we try so hard to force our work into these idealized project planning methods. And the question is, why don't we simply accept function differently as humans and create a framework that best accommodate this? And a framework that help real teams reach their goals and as quickly and as effectively as possible. And this is basically the core idea behind Agile methods. So we no longer pretend we can plan things, we regularly find out we actually cannot. And in this webinar, I'll share the ideas and insights of Agile working, focusing especially on how we can meaningfully apply them in the hardware development environment and in our daily lives. But before we go into the topic, I understand that there are also some reservations about this topic. On one hand, because probably many methods of Agile software development cannot simply be transferred to hardware without adjusting them. And on the other hand, because some people have already had bad or negative experiences with agility, Scrum, Kanban, and so on. But in most cases, this is because these methods were not implemented as they originally intended. And so at the beginning of this webinar, I have two major requests for you. First, please be patient for a moment as I discuss the basic ideas. I'll soon get to how they can be implemented to hardware development. And second, for the next 30, 40 minutes, please set aside any past experiences you or your colleagues may have had. I want to show you that these experiences have little to do with the actual principles of agility. And before we dive fully into the topic, a quick introduction about myself. I'm Elias Vögel, co-founder of Multivative from Austria. We develop and build machines for automated electronics prototyping. I have a few slides on that at the very end, but now let's focus on Agile electronics development. So the core idea of Agile development is that we accept the inherent characteristics of people and their ways of working as a given, and to build an optimal development process around them instead of doing it the other way around. We accept that humans are generally poor at estimating the durations of tasks in advance. However, we still need some sort of planning in a project in some way. We cannot just dive into it and see what happens. And even in an agile world, we do this, of course, but at a much higher level of abstraction, at a higher flying altitude than we do it in a traditional way. We still define what we want to achieve, who wants a feature, what is it about, why it is necessary in general, and very important also the definition of done. So when is a task considered complete? We also estimate the size of tasks in Scrum, for example. We don't do this absolutely, but relatively. I already mentioned it. Studies have shown that while we are really bad at estimating absolute time durations, we are fairly good at comparing things and comparing tasks in regards of their size. And so we can choose other ways of assigning sizes to tasks instead of doing absolute time estimations. For example, we can use T-shirt sizes from XS to XL or other ways. And one key difference between agile planning and traditional planning is that we accept from the start that the plan is wrong, but it's still the best we can come up with at the moment. And that might sound frustrating when you hear that first, but the only thing I can think of that is more frustrating is treating a flawed plan as if it were the truth. So it's then much better to at least know that it has to be improved throughout the project. Some words about the agile process, how it actually works and how it is compared to the traditional waterfall process. The plan is to implement projects in numerous cycles. The primary goal is that we have at the end of each cycle a usable product available that improves from every iteration to every iteration and can then be tested together with users to gather feedback from them that can then be used for the next cycle to further improve the product. And at the start of a cycle, it is decided which tasks will be implemented in this round. And at the end of a cycle, there is time for reflection on it went, if there were any issues that are currently causing problems, what is working well and should be continued. Also on the level of the process itself. So we are also thinking about how we can improve the process, the development process itself, but I'll come to that later on. In the early 2000s, the quite famous Agile Manifesto, you've probably heard of it, has been written down, somewhat the start of things like Scrum. And the Agile Manifesto consists of 4 basic sentences, and those are the ones that are on the slide. And they compare individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, responding to change over following a plan. And what's very important to understand here is it's not the one or the other. It's not individuals and interactions instead of processes and tools, but it's the left side of those sentences is slightly more valuable than and more focused on than the right side. And many people think or say, we cannot do this, we need documentation. And of course you need documentation, but if you think of a real life project, working software is always more important than a comprehensive documentation, because the best documentation is worth nothing if the software doesn't work or does not fit the purpose it was planned to. And so it's not one or the other, but the left side is more important and is put a bit more focus onto. It's also very interesting to get an idea of how everything came up. And the start of Agile ideas were actually in hardware and even in manufacturing, which is very interesting if you think about it. And many see that the Toyota production system, short TPS, is somewhat the start of those ideas. And Toyota during or after the Second World War had massive problems regarding getting resources, because it was difficult in Japan in that time. And so they had the goal to minimize the waste in their production and limit the buffers to an absolute minimum between the single production stations. And so they came up what we now call just-in-time production, always keeping in mind that to have small sizes that are very small, lot sizes that are very small. And they changed from a centrally controlled push system, where at the center it's decided which production station has to produce how many items. And they switched to a pull system controlled by Kanban, where every production station controls the output of the previous production station in order to keep the buffers low. And you now might ask, what does this production system has in common with development? But you can think of development as a serious production of finished features or tasks. And when you do that, we basically have similar goals. We don't want waste in our development series production, and we don't want buffers, because buffers are nothing else than unfinished goods, or in our case, unfinished tasks or features that lie somewhere in the process, but can't generate value to the company or to the customer because they are not finished. They're not in the version of a product we can sell and generate revenue with. And so we also try to minimize the waste in our production. And waste is everything that slows down our development team in their work. And there are a few points that I want to outline here. And the very first one is multitasking. In many companies, people work on several projects at the same time, but studies show that if you work on 3 projects at the same time, your performance, your productivity drops by 40%, just by the context switch losses you automatically have if you have to switch between the projects. And so that means if you have in your company, your teams work on 3 projects at the same time, you could almost do double the project if you would do it one after the other. A second very important point is that half finished is not finished at all, which means if you have tasks that are almost done, you have to treat them as not done at all, because it cannot generate value. And that also leads to the idea that to minimize the task, same as again as in the in the production system, to have as many finished tasks as early as possible. Also, an interesting number backed by studies is that if you solve problems or errors immediately, it will be much faster than doing it later on. Studies show that if you do it weeks later, it will be about 24 times longer because you have to think again into the whole system and to the whole problem. So it's very important to have some kind of automated testing to find those flaws and errors as early as possible, as early as you can utilize the fact that you are faster in fixing it because it's the implementation is not long ago. And of course, we want to remove unnecessary reportings and stuff like that. And very important point, we have the idea that we want to constantly improve our process. Again, compare it to the production, where they always try to improve the flow of the production to generate as much outcome. And we should do the same in development, not just taking the development process for granted or for given, but improve it along the way. It's the development process is a core product of a development team as well. And speaking about teams, studies show that the ideal team is an interdisciplinary, autonomous, and small one. The optimal size of teams is up to 7 members, and bigger teams lead to a reduced performance, which is caused by more overhead regarding communication and so on. In order to be autonomous, it's important that teams have a clear goal and somewhat of a greater meaning of their work, because it helps to make decisions on their own and not being dependent on decision making of a higher management layer. And interdisciplinarity is also a huge point, because it's much more effective to have a team that contains all the disciplines that are needed for finishing the project, instead of having a software team, an electronics team, a mechanical team that are all working on several projects at the same time. It's basically the same reason as for the first point. It's communication. If you have all the team members together in one team, it's much easier to get along with each other and being up to date and keeping the others up to date, and just reducing the communication overhead. Which also means that thinking of the ideal team size of 7 people, we have to split bigger products that cannot just be implemented by 7 engineers on their own, have to be split into several parts, but I'll come to that later on. Now going into Agile hardware, more specifically, McKinsey has performed a very interesting study last year, 2023, about, and they compared and worked together with 20 companies across the different sectors of electronics industry, from consumer to automotive, medical, industry, advanced electronics. And what they found out is that the average time to market acceleration was about 30% of the companies that switched from a traditional to an agile development methodology. And that by improving quality by 20% on average, the simplicity increased by 40%, the productivity increased by 20%, the predictability increased by 50%, which is a very interesting factor when you think of or when you hear arguments like we have to follow traditional methods because we cannot just go into the project without detailed planning, because we have to predict everything. And now studies show that agile methods actually help you to be more predictable. And also employee satisfaction went up by almost 20% on average. So there are a lot of reasons to think about this and trying to implement that in your team. But if it were easy, everyone would probably be doing it. But it's much harder than in software, for example, because in hardware you have to have often to do physical prototypes to test things. Testing costs time and money. Also, when you do simulations, it's often a lot of work to do to get good results and meaningful results. And also formalities can hinder agile ideas in practice, for example, in medical or safety applications. That it's not that easy as in software development, for example. There's a very interesting book on this topic and on best practices, which is in the literature list at the end of the presentation. I'll go into some of those topics right now, but you can read into it afterwards on your own into the remaining parts. But I'll go into the most important ones. And one of the core ideas behind Agile hardware is the so-called increment. And an increment is each new usable version of your product. And an increment can be used for testing, for validation, and to gather feedback from actual users to further improve in the next increment. An increment can be a physical product, but it does not need to be one. Also, other versions of your product can be used for validation, for example, simulations or other things, easy or simpler prototypes, for example. And it's often difficult to get an idea of how valuable is time during the development or in a development project. And therefore, I highly recommend to use the tool of cost of delay, which is basically a uniform currency for measures and delays inside a project, which is calculated in euros or dollars. And it can be used because everything you do or not do influences either the cost side or the revenue side. And if you know how much one day of delay in your market entry costs your company, it's a very pragmatic tool for teams to make their own decisions because it's an easy calculation for them. If the whole company has decided on this specific day. Just to give you a short example, if you wait for, or if you need a part very desperately, and you cannot advance further in your project, and you're thinking of paying extra fees to get it faster, get faster shipping, and this extra fee costs you 2,000 euros. But you also know that every day cost of delay costs you 10,000 euros. It's not really, or it's not a hard decision then. And in or examples in real life scenarios show that the cost of delay is usually in the 10,000s of euros, also for medium-sized companies. And it's calculated by, on the one side, using the missed revenue due to a delayed launch of the product, and also by utilizing the increased cost due to delays and then a longer development time. And it cannot be specifically calculated. It's always an estimation, but it already helps if you have a brief idea of a size in which your cost of delay is. So what do we try now? We we as a development team try to minimize the increment. And there are several things we can do to achieve that. And one of the most powerful things is to have a modular architecture. I have a whole slide on this topic, so I'll go into that later on. We can also optimize the prototype purchasing for time instead of cost. So the cost of delay is usually higher than higher expenses to get faster prototypes. Then there is the option to do automated hardware testing early on. Again, I already mentioned the fact that you need much lower time if you fix bugs early on. So automated testing helps there because you find them very quickly. We can do simulation and we can do rapid prototyping. I'll go into both topics in a few slides. But first, modular architecture. That's in my view, it's the most powerful tool we as engineers have, and it's also the key enabler for agile electronics. Because if you divide your product into modules with standardized interfaces in between them, it allows us to do quick changes of single modules. So it's so we design for change. We right from the beginning, we accept that we have to change our concepts and plans throughout the project, and we focus on a design that enables and allows this change right from the beginning. One key advantage of a modular architecture is that we can have sub-modules that are in different development stages. And we can also do design freezes step by step. For example, if we have an architecture where we have one module that is specifically critical due to legislation or formalities, testing, certification, or stuff like that, we can start with this module. And while this module is certified, we can start with the HMI user interface, power supply modules at the same time. So the most critical part is already in certification, while we can constantly improve on the other parts that are not that critical. And we can also have different teams work on different submodules. And here it's now possible to have these smaller teams that work on single modules. And also having in mind that we want a team of about 6, 7, 8 people, an interdisciplinary team working on a module. And if you have such a modular architecture, that's now possible. One disadvantage of a modular architecture, of course, is that it might be more expensive, at least if we mass produce the product. But we can always do another iteration where we combine different modules or maybe all of them on a later stage when we know there won't be much change anymore, and so aim for a cost reduction later in the project development. And there are some, of course, for a design for change, we also slightly more like FPGAs instead of ASICs and connectors instead of solar connections and stuff like that. Just doing measures that eases the modularity and changing of the architecture and of the product. Here we have an example of such a modular architecture. Here it's a camera with housing and electronics inside, and we can, for example, also have different stages in mechanical engineering, electronics engineering in parallel, and combine it in between and also at the end of the development phase. And as mentioned before, we can we can do iterative design freezes. We can freeze the design of critical parts that need longer certification times early on. We can also, for example, do parts that are not allowed or is hard to implement Agile methods in waterfall methods because of formalities, legislation, and the other in a more Agile way. That's the flexibility you get when you design your product in a modular architecture. What can often be seen in development departments is something Joachim Pfeffer calls framework arithmetic in his book, and I think it's a very good term that describes what's the problem, because in the beginning we think of what we might need and put everything into the bag of requirements that might be required at the end, because we do the electronic ones and don't want to add something in the end, and we probably aim to add a little bit more to the requirements than we actually know that will be necessary. And what really happens is that you still have change requests in your project, and then we have a high quantity of parts in your architecture, on your PCB, for example, in your circuit, that is never actually used by firmware, for example, or by a user or a software or something like else. And so features that were, or we thought would be important in the beginning, might never be used. And it's especially dangerous in teams where an electronics department is separated to a firmware development department. And then it can happen that we put all kinds of sensors and interfaces to the board, because firmware says, yeah, we might need them later on. And in the end, we only need 30% of the hardware. And so if we synchronize that process and only put those things into the requirements that we actually know that we need, we only need those parts of a framework, or we only build those parts of a framework that we actually need. As mentioned, automated tests are very helpful, and there also the modular architecture helps, because we have standardized interfaces that we can use for testing. We can test single modules or single submodules, and use the test setup also for hardware versions in future iterations, because if you have a standardized interface, it's not really important if, for example, in the next interface we have an ASIC instead of an FPGA, as long as the interface is the same. And as mentioned before, it's much easier to find or to fix errors early on. Also important, simulations. And the best case is to use it in those areas where it's easy to do. It's always a trade-off between building physical prototypes and do simulations, and it highly depends on how much prototypes cost and how difficult simulations are in practice. And of course, that's totally different if you're doing chip design or PCB design or other parts in hardware engineering. But one key advantage of simulation is, of course, you can automate it. You can build pipelines similar to software development, which is, of course, great, because then you can automate the testing of parts in every iteration. But of course, many parts cannot be tested with simulations, and there comes prototypes into play. And I want to divide prototypes into three main stages, or three main kinds. The first one are feasibility prototypes. They're done very early in the feature development, and the goal there is to reduce the risk very early on. Those prototypes can be very simple test setups, can look like in the picture on the slide, and they're just here to do an basic feasibility estimation of technology and requirements, to get an idea how risky is it, possible, how big is the risk, and also to prioritize different tasks according to the risk. The second stage are simpler user prototypes, and that's often the stage that is not really done in practice. The goal here is to recognize early if a feature or product or parts of a product generate value for users. And here prototypes don't look like a final product at all. We don't consider final space requirements, handling, user interface, or anything like that. But we want to test single features to find out if our assumptions on which our requirements are based are true. Also, the requirements regarding quality are not as high as as later on in the development. And it's very important to take those prototypes and test them together with actual users. And we also do that in our practice, and it really helps to avoid unnecessary development times of features we thought would be helpful, but weren't really needed by the user in reality. And if you find that out after a few weeks, it's much better than finding that out if you have implemented it in a final product a month later. And the final stage of prototyping are the advanced user prototypes, where we have the goal to learn the value of a whole system, an advanced developed product for users. It's like an A series, B series, A prototype, B prototype. And here we already have most of the features of an aspect of a final product. But if we find out that features are not really necessary on this stage, it's basically already too late. That should be found out on the stages before. So it's here we want to know if some parts need to be reworked or put special attention to on the final weeks or month until the series production is started. And I have some best practices for regarding the prototyping stage. And one of the most important one is to think of how can we validate an aspect of a product in the most simple way. And here it really helps to also talk to others, because of course as an engineer we are or we want to achieve perfect solutions. But me and my colleagues often helps to talk to other people. For example, talk to a software engineer as a hardware engineer myself, and ask what he would or she would do to validate this idea. And it's not important how it looks, or if it looks perfect, if you would show it to other companies or other colleagues. It's just important if you find out what you want to test, the assumption you want to test. Also, according to that, act as fast and simple as possible. Decide on the quality requirements depending on the stage your prototypes are in. So for example, for early prototypes, you don't need the quality as for the final prototypes. You maybe want to choose different purchasing or do some of them in-house, and the later prototypes on your serious manufacturer to already test them on their machines and SMT assembly lines. And also use unconventional approaches. Think outside the box and think what is the minimum possible way to get the information you want. And also prioritize the prototyping work you want to do or you think is necessary, and validate the biggest risk first to get a clear picture in which direction you have to go and in which accordingly. And yeah, perfectionism is often the wrong approach in regarding prototyping, especially in early stages. There's often the challenge to synchronize hardware and software engineering, and there are also some solutions to that. For example, MIT professor Steven Eppinger presented the idea of decoupled sprints, so that the hardware and software teams have different iteration lengths, or also alternating iteration length in the hardware teams, to accommodate to the fact that in hardware we also have to do prototyping that is not as fast as hitting a button and waiting for the compiler to finish a software build. There are some frameworks you can utilize, but I don't want to go into detail of those frameworks a lot, because yeah, there are different frameworks out there, and you have to decide which fit your current situation or your team, your products are best. One of the Agile frameworks that are specifically for hardware is MAHD, which introduces sprints inside of or iterations inside of iterations to have those integration, prototyping, alignment phases built into the framework itself. So yeah, we have a framework that is specifically targeted for hardware teams, has room for a bit more planning regarding architecture and so on. Also, the fact that in hardware we often have to integrate suppliers and other stakeholders into the whole process, which is often not necessary in software. And so, as we are getting to the end, some short information, a bit of information about what are we doing. We are, or during our education and work, we found out that there are basically two different ways of doing electronic prototyping. One is to outsource it to SMT manufacturing lines, and the other option is to have a semi-automatic assembly or automatic assembly in your own office or in your own company. And both are quite costly and take a lot of time, and that holds back electronic development, because as mentioned earlier, prototypes are a huge bottleneck in electronics development. And so our solution to that is a machine that combines the different manufacturing steps that are normally done in an SMT manufacturing line into one single machine. So we do the dispensing of solar paste, the picking placing of components, the soldering, the AOI process, and so on in one single machine. And you just put your data into it and the components and the PCB and the raw PCB, and get a soldered and verified PCB out of the machine, similar to you work with 3D printers and so on. So we want to enable companies and also EMS companies to improve and accelerate their electronics prototyping, because the serious machines that are out there are not targeted for those very low quantities. And quite new information, we are also launching our pick and place prototype assembly service with our own machines we have here at our office with picktoplace.com at the beginning of next year. So to also having a possibility to share the advantages of our machine to smaller companies or companies that don't want to do the investment of having an own machine. So feel free to go to the website and enter your email to be kept up to date, and we will be very happy to produce your prototypes fast and simple. So at the end, I have some very interesting literature for you that helps to go deeper into the whole topic. I can highly recommend the book from Joachim Pfeffer, Produktentwicklung Lean und Agile, the book from Michael Keir and David Eden, Agile Hardware Product Realization, and also the book from Jeff Sutherland, which is the founder or the one who introduced Scrum, which is used in software. The Art of Doing Twice the Work in Half the Time. It's not specifically targeted on software development. Of course, the core ideas come from there, but you can apply a lot of the things he mentioned in the book also for hardware development or for other parts of your life. And I have some studies like the McKinsey study. There is an interesting study from the Boston Consulting Group, also interesting information from Alcium and MAHD as mentioned before. And yeah, finally, I want to say that becoming agile in the development is not just about implementing a framework. It's a transformation in your whole process and also the way you think as a company. So it's in my view, it's very important that it also is supported by the leadership of a company, because yeah, you need things like, or be aware of things like cost of delay to value the advantages of agile electronics and agile development in general. Thank you very much for listening. And now I'm very happy to answer your questions. Thank you very much.